Hi, and welcome to the Consulting Specifying Engineer Webcast, Specifying Generator Set Paralleling Control, sponsored by Cummins. I'm your moderator, Gary Cohen. Happy to join you today on behalf of Consulting Specifying Engineer and CFE Media and Technology. Before we really dive in here, let me give you some tips and tricks to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, simply refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you're having technical problems with audio or the slide presentation, just click on the question mark at the top right corner of your screen to access the list of system checks to try. If you do need a technician, type a message in the Ask a Question box and the tech team will get back to you as quickly as possible. Individual user experience questions will also be answered in that Answered Questions box. Now, if you do have questions for the speakers, just type those in the Ask a Question box on the left-hand side of your screen. The live Q&A session will start in about 45 minutes. Today's webcast is being recorded, and you'll receive an email within a week with the link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. Now we're going to hear a little bit from the sponsor of today's webcast, Cummins. At the conclusion of this video, you may experience a few seconds of silence. That's just to compensate for varied internet speeds. So please stay tuned after the video for today's presentation.
There is a critical balance between power and control. The need to take control of power in a microsecond. Cummins engineers know reliable power is only possible with digital control. Applying digital engineering to decades of experience, studying every possible anomaly, from simple power systems to the most complex. Isolating up to 1,200 hypothetical failure modes, all to meet one objective: totally reliable power. Digital master controls built with human intelligence.
All right, let's get started. I am happy to introduce today's presenter, Hassan Obaid. Hassan is, let me click over one here. There we go. Hassan is a global technical advisor for systems and controls, critical protection at Cummins Power Generation, focusing on technical vision, business strategy, and solving a wide range of complex problems. Hassan has been with Cummins since 2007 in a variety of roles: power systems design engineering, project engineering, and application engineering. He has designed power systems involving switchgear, controls, paralleling, transfer switches, generator sets, and digital solutions. He's developed and conducted numerous technical power seminars to consultant engineers across the globe on several topics and products involving paralleling, grounding, power systems, and controls. He led the switchgear design for the Bear 800 kilowatt mobile power unit for the Air Force. He received his bachelor's degree in computer science and master's degree in electrical engineering from Minnesota State University, Mankato. Thank you for joining us today, Hassan, and let's go ahead and get started. I'll turn things over to you.
Thank you, Gary. Thank you for hosting us today. Good morning, good afternoon, and good evening to all of you. Thank you for joining us today. I'll start with just a quick map, depending on where you are in the country. If you need access or you need help with your applications, what about paralleling, switchgear, transfer switches, or system designs, please reach out to the folks that you see here on this map, and you'll get a copy of the presentation so you don't need to write this information down. We have to start with a disclaimer, so I have to read this verbatim for you before we start. The views and opinions expressed in this course shall not be considered the official position of any regulatory organization and shall not be considered to be, nor be relied upon as a formal interpretation. Participants are encouraged to refer to the entire text of all referenced documents. In addition, when in doubt, always reach out to your HJ. With that out of the way, now we can get started with our course, which is Specifying Generator Set Paralleling. Will provide you with a comprehensive overview of paralleling generator sets in the power system. So we'll start from a high level, then dive down a little bit into the controls and the fundamentals of the controls that are needed to parallel generator sets. I do have a slide for you on paralleling generators with the utility. And then we'll talk about traditional paralleling and compare that with the distributed logic architecture. So the objectives are to review basic paralleling controls to gain better understanding of how paralleling is accomplished. Understand how generator set control functions are provided in a distributed logic architecture to improve the reliability of the system. And we'll learn about the benefits of distributed logic architecture as it relates to paralleling, system reliability, and ability to eliminate single point of failure. And at the end, I have this one use case to share with you. So if you've attended some of my webinars, I always like to start with the basic components of a power system. So I call those are the pieces of the puzzle, right? So you have sources, that's a utility, a generator set that's a diesel or natural gas, or it could be a renewable source. We'll have power switching equipment, commonly known as a transfer switch. And we have what's called distribution boards and system level control or supervisory control. And the distribution board, the term that you most commonly use is switchgear. And technically switchgear falls under, the code is 1558, and which is typically designed in a lot of circumstances to handle up to 30 cycles of short time rating. And then there's a switchboard, UL891, and like I said, in some applications, you'll have a system level controller. And for a world that is completely connected nowadays, and to make sure that our sites are up and running, some kind of a reporting cloud connectivity for diagnostics, compliance reports, and push notifications, and also to make sure that we send the right technician with the right tool at the right time to solve any of the problems. This is when we need some level of cloud connectivity or remote monitoring systems. From these pieces of the puzzle, we can have all of them, or we can have some of these pieces of the puzzle that we put together to design our power system. So when you're designing your system, you're specifying, and the specifications that you use are this 2600 in the section in the master spec, and you hear they're named paralleling a switchgear, and it could be medium voltage or low voltage, and you write about anywhere between 20 to 30 to 35 pages long of specification. I would love for us to dive into every single line item, but we don't have time. It's going to take us a week to do all that. But I do have a little bit of, I'm going to cover 1 or 2 slides or about 3 slides about traditional paralleling and traditional specifications and how we specify paralleling systems today. So out of the specification, you'll have a system that might look like this, and this is your paralleling power system. So you specify, you need to know that you're specifying a system, right? Not specifying an equipment. You're specifying an entire system. So your system, you'll have the sources, you'll have the backup generators, we'll have the paralleling gear. And today I'm going to explain my opinion on why we call it paralleling gear and why I don't want to call it a paralleling gear, because the controls are not in it. The controls are somewhere else. And you'll have a supervisory controller in some systems, and you'll have transfer switches. The focus for us today will be right here on the generator set paralleling and the power of the switchgear or the distribution board. So the details, so in here, let's just break up into 3 layers. So right here in the center of this page, you have this 1-line diagram that you're designing, and you're working on all the details of the calculations. And right on the top right-hand corner, here's the backup generators with the paralleling gear, and then the transfer switches, and here's the utility. So this is the details that we're working on. But from a very high level, at the end of the day, what we're doing is we're designing power systems, for example, for a water plant that's providing clean water to our citizens, or for a water pump station to prevent, for example, a city from getting flooded. Or it's for a hospital where somebody's under the knife and going under a surgery, undergoing a surgery, or it could be for a critical infrastructure such as airport, and we're trying at the end of the day to get travelers from one location into another, right? So this is from a very high level of what we're doing. And in the bottom level, at the lower level here, you're doing the design, you're trying to figure out where the power is going to. And then in the middle level, when you're specifying a system, right? what we're specifying is the things that we want to specify from a high level is we want to specify seamless system integration. Remember, we're specifying the generators, the gear, the transfer switches, and that entire piece together. We want to specify a seamless paralleling operation. I'll explain what that means later. Seamless paralleling operation if a generator set fails during a start or while paralleled. If we have 5 gensets paralleled and genset number 3 decided to go out to lunch that day, we don't want that entire fleet of gensets to stop working because that genset is not happy that day. We want to eliminate single point of failure, and then we need to have some level of protection, and we need to have a comprehensive level of metering and diagnostics. And we want to have some kind of a capacity to load consumption optimization to reduce the wear and tear on a generator set and also reduce fuel consumption. So those are kind of the high level that we want to specify or we want to think about when we're specifying this paralleling system. So now that's out of the way, let's start diving into the details. So we're going to start with paralleling. Here you're looking at a one-line diagram of a very typical system of what's called an isolated bus. You have 3 generator sets, a few transfer switches, and here is the utility. And by the way, so in this presentation, we're assuming that you've made the decision to parallel gensets. We're going to talk about, this is why it's called paralleling generator sets. So we will not discuss whether we need a generator, whether we need to do paralleling or not. So the assumption is that we need to parallel and how do we achieve paralleling. So paralleling is what we say is a synchronous operation of 2 or more generator sets connected together. Synchronous operation because we can really correlate that sinusoidal wave, the output from the genset, to the position of where the rotor is inside that stator. And we can also correlate that frequency, for example, 60 hertz to the number of poles and to the number of rotations. So typically the most generators, all the alternators that you'll be dealing with specifying are 4-pole generators. And so for 60 hertz, the RPMs would be 1800 RPM, right? This is applications for North America for 60 hertz applications. You might say, okay, well, what are the advantages of paralleling? Obviously, the performance. The more generator sets you have connected to the bus, the stronger, the stiffer the bus, the more you'd look like a utility. It's easy to create what's called an N+1 or redundant system, right? All you got to do is add 1 or more generator. Serviceability. Hopefully, you're doing regular maintenance on the generators. And for example, if you have 1 generator and you want to take it down for maintenance, you don't have backup power. So this is why you want to resort to adding 2 or more generator sets, and obviously reliability. You might ask the question though, even though the discussion is about paralleling, is why I don't want to parallel. And I would say the number one probably reason is cost, right? Is you don't want to add another generator and your application doesn't need it, right? Obviously, if it's a hospital of a critical infrastructure, yes, you would want to specify redundancy or a data center. But for example, if we probably have a generator for a grocery store or maybe for cost cutters, we probably don't need to have multiple generators to parallel to feed that load, right? So it really depends on the application. But really, there's no downside to paralleling generator sets. So when it comes to paralleling, we're going to do high level, then dive down a little bit. And since you're going to earn a PDH from this course, so we're going to have to talk a little bit technical information. And so it's going to get a little dicey, but that's okay because you can handle it. So for paralleling generators, from a very high level, we need a point of common connection, a point of power connection. These are where the cables are connected, right? This is the point where the generators are providing power to the loads, and this is what they reference when they connect together, reference that voltage and reference that, do the sensing. We need electrically operated circuit breakers, and these circuit breakers, we need 1 per generator. We can't get away without electrically operated circuit breaker. It's for when we're in sync, we want to close, and also it acts as an isolation if we need to disconnect a generator. We need to have some kind of an arbitration to arbitrate if I have a fleet of 2 or more or 17 gensets and they're all ready to close and connect to this bus right here, to this common point of connection. We need to determine arbitrate which one closes to the bus first. And then if one of them closes to the bus first, because the bus in this case is de-energized, let's say it's a black start. So this is why we need the arbitration. And once the one closes to the bus, the next thing we need to do is we need to synchronize. So we need to synchronize the phase, voltage, and frequency. And this is why we need to sense, this is why I have the potential transformer in here. If it's a high voltage, or it could be some generators that controls, they can sense up to 600 volts directly off the bus. Once you're synchronized and the magnetic flux is coupled between the alternators, they're running like one machine now, so we don't have to worry about that. The next thing we need to do is we need to think about load sharing. And with load sharing, have to share both the real and reactive power equally amongst the generators. And we're going to talk about isochronous versus droop. And then there's need to be some kind of a protection. And I have a slide to talk about generator set protection. Things like sync check, reverse power, over voltage, under voltage, over frequency, under frequency, reverse reactive power as well. And we need to have some kind of a metering and diagnostics and alarms. So what I'm going to do next is that, so we talked about the point of common connection, electrically operated circuit breakers, and this arbitration. Now I'm going to start talking about the next three levels, and then I'll talk about how do we achieve that with the controls? What is needed to achieve that? Connecting AC sources. So when we connect AC sources, and let's just say we're going to connect a generator output to another generator, we can only do that when three conditions are met. And I'm sorry here, I'm showing everything on the slide. I'm not stepping through it, is just to account for different bandwidths and internet speeds. So the three things that we always need to check when we're connecting two AC sources is we need to make sure that the frequency or the speed between those two sources is matched or within a 1/10 of a hertz, for example. The phase angle difference between the two also must be kept to a minimum, say plus minus 10 degrees or plus minus 8 degrees or so. And then the voltage amplitude, the difference between the two, should be also kept to a minimum, say plus minus 5% or 10%. If we don't do that, the one with the higher potential, for example, in here, you can see that at this time, at this angle right here, the green wave is at a higher potential, or at T1 in here, the green wave is again at its max. The one with the higher potential is going to push the one with the lower potential, right? So then you're going to have pushing current or push the other source around. And this is why I want to keep that to a minimum. Handling those speed, phase, and voltage amplitude is called synchronization. Talk about that next. But there are two other factors we need to consider. There is the waveform, which is when you're specifying alternators or generators, you probably heard the term 2/3 and 5/6, and this has to do with how the generator is constructed. And that only comes into play if you're specifying a new system. Obviously, the manufacturer will make sure that it's a 2/3 pitch, and most generators out there are 2/3 pitch, but some are not. The issue comes in if you already have a genset in the field and you're doing expansion. So maybe you have a genset, you have an application with the first two gensets you installed, those two gensets were installed in 1950s, and then two more added on in the 1970s, and now you're going to buy today two more generator. We want to make sure that the winding pitch matches. If it's not, there are ways around it. The problem is a 2/3, not a problem, but the thing is about a 2/3 eliminates the third harmonic current versus a 5/6 does not. So we want to make sure we handle that appropriately. And so you only have to worry about that if you're going to a brownfield. And then there's obviously there's the phase sequence. Phase sequence, we only have to worry about it is when we commission the system and we run the cables. And obviously the controls nowadays are very smart to detect out of sequences that are out of phase. So for us, we're going to assume that those factors are okay. We looked into those. So now every time we start the generator, we want to close it into another AC source, we have to synchronize. So by that, synchronizing is the mechanism by which we match phase, voltage, and frequency. And we have to match these three elements. And later on, I'll describe what are the controls that are needed to handle the synchronizing those three elements. So this is synchronization. Now that this, once the two generators are, let's just say what we have two gensets that we're going to parallel. Let's say that the two sources now are paralleled. Their magnetic fields are coupled and the flux is connected and they're running as one machine. We need to think about load sharing. So your loads will demand both. Your loads are not completely resistive and they're not completely reactive, right? So that you need to provide a lot of times both real and reactive power. And so typically the engine is where the real power comes in and the alternator is where the reactive power comes in. And load sharing is, what is load sharing is dividing that load equally amongst the generators. If we don't do that, we will have problems with stability of the generators. If the one with the, if you look in this drawing here with the two generators at one line with the hertz imbalance and voltage imbalance, if we don't share the load equally or have some kind of a smart mechanism to handle that, the generator with the higher power will be pushing the other one. And it will cause it to shut down and reverse power. So we want to make sure that we have effective means to do load sharing. Load sharing that can be what's called isochronous or can be droop. If the difference between the two is that isochronous, if you look at this diagram here in the middle where we have percent hertz in the lower portion of the slide, the percent hertz or volts versus the percent load. With isochronous load sharing, your output voltage, let's just say a 480, does not change whether you're 0% loaded, 50%, 80%, or 100%. You're still going to get 480. You're still going to get 100% of that voltage. The same thing with frequency. So your frequency does not vary as the load varies. Droop, on the other hand, is this red line that you see in here. Your output voltage and frequency will vary as your load varies. So for example, at 0% loaded, your frequency might be 61 hertz. You set it up to be that. And your voltage is, let's say, 490. And then when you're 50% loaded, you're at 60 hertz and at 480. And then when you're 100%, you're something lower than that, 59 hertz, for example, 59.5 hertz. Obviously, once I describe this to you, you're probably thinking, okay, well, I want to stick with isochronous, and this is more the preferred way, and this is what we see the specs is asking for, isochronous. Isochronous is the more advanced mechanism to do load sharing. However, it requires communication between the generators. We have to run cables for one conductor with one cable, 4 conductors inside of it shielded, 2 for the VARs and 2 for the KW. The droop, on the other hand, does not require the generator sets to communicate with one another. And this is, for example, if you have 2 generators from 2 different manufacturers, and there isn't some manufacturers they have ways to do load share between the different generators. If they don't have that mechanism, we have to resort into droop paralleling. And then there is also the protection. So this is load sharing. There's the protection. As a minimum, we need to protect against reverse KW, reverse reactive power. And then there's a synchronizer, sync checks, under voltage, over voltage, phase sequence imbalance. The numbers that you see in here are the ANSI designation numbers. You can look those online and get a list of all these numbers. But as a minimum, we need to have some kind of a protection on the generator sets. So we talked about the controls and what we need to do to control the system. On any generator, there are, I'm going to call 2 knobs. And those 2 knobs are the governor and the voltage regulator. The governor is what maintains the engine output speed. The voltage regulator is what maintains the output voltage of the generator. How does it work? Is that, here's, for example, the governor. We send the fuel injector some PWM signal. It's putting some kind of a fuel level. If we If we need to increase the torque, if we need to pick up more kW, what we do is we change that pulse of that signal, and now we get more fuel, we get more power out of the engine, right? So this is how we control the torque or the real power from the generator, from the engine. On the other hand, from the generator, here is, for example, here's the rotor, here's the stator. We can change the output voltage. Let's say that we want to go from 480 to 490, or from 490 down to 460. What we do is we just invoke Faraday's law. We change that DC field where the rotor is spinning, that's cutting those field lines, and I can get higher voltage. Or if I want to go down to a lower voltage, all I need to do is decrease that DC field, and then that output voltage changes, goes lower. Okay, so if we could tie it back to synchronization, right? So synchronization, to synchronize phase and frequency, I'll just give you the answer, we control the fuel. So by controlling the fueling, I can, if I have a set point, for example, 1800 RPMs, and the fuel is coming in, we're sensing that governor, that engine governor sets that fuel for me, sets that engine speed and maintains that at 1800 RPMs. Now, if I need to change that output voltage from the generator, and I need to get a little bit higher voltage or reduce the voltage to match the other source that's online, again, I have a set point, and then I change that DC field that goes from one source, the DC field that goes into that rotor that cuts through the stator where that output voltage is generated, or induced, I should say, the most technical term. So now putting the two together, if this is my generator, this is the prime mover, which is the engine, real power, and this is the electric generator, and they're all connected on the same chip, they're coupled together, and I get the AC output voltage with three-phase voltage. It was basically, I have two set points, and then I change that offset. So that's what the control is doing. Okay, so now let's tie this into paralleling. I was luckily just the last 2 weeks, I've actually came across 3 different projects with specs on my desk right here. Each spec was about 30, 40 pages long, so I don't have time to discuss them all. So I just put down some of the things that caught my attention. So traditional paralleling specification, the things that just jumped at me that I saw in there, that as you can see in here, it says generator set control and monitoring, provide analog devices for voltmeter and frequency meters, provide switches or other provisions to allow reading for both generator set and the bus. And then I saw things calling for 360-degree analog movement for the synchroscope, sync lights, and then it asked for an individual section for paralleling controls for every generator and a master level control. So traditional paralleling control and design, it starts out with the paralleling control R in the switchgear. There is a master level controller. It's component-based design, and it's a PLC-based. So the design is a PLC-based with lots of wiring, and it's what we call is a nightmare to troubleshoot and design. So component-based, you have a separate component for every function. So every function that I just described, for paralleling, for controlling the phase, for controlling the excitation, for controlling the fueling for the engine, protection, every arbitration, every single element had to have its own component to do so. However, the elements for paralleling control are, we need to have something to control the speed, kW. This is done by the governor. What we need is we need to control the voltage, so the VAR control. And we need to do what's called the arbitration that I just talked about, basically deciding on which generator set closest to the bus first. And we need to have some kind of protection and metering. So we looked at what we need to control, and then we looked at traditional design, how it's done, and now how is it accomplished in a integrated autonomous paralleling, is that all the functions that I just described actually resides on one controller on the generator set control. So here's a generator set with what's called a generator set control box, and inside of it there is this microprocessor-based control, and then there is the human machine interface, or the HMI. And the generator set control is responsible for doing all the paralleling functions that I just described. So if we take a closer look, here we have the HMI, the human machine interface. From there, the operator is able to, it's a way for the operator to interact with the machine, user interface, configure, look at the settings, receive alarms, start, stop the generator if they need to, and perform what's called manual paralleling. The generator set control, this integrated controller that is on the generator, it is responsible for the first start arbitration, right? Which is basically dictating which generator set closest to the bus first. It's responsible for synchronization, phase, voltage, and frequency. So it has that synchronizer built in, and it's obviously, and it's a 2-input synchronizer. So it's looking at the line side, and we need to connect the load side after that paralleling breaker. It's doing the voltage regulation. It's obviously, and then it's doing the load sharing, the kW and the VARs. You might ask a question, well, what if I have generators of different sizes, a 1 megawatt, a 2 megawatt, and a half megawatt? Can a controller do load share equally? Yes. The genset will also share the load equally amongst the generators. So the larger the generator, the more load it takes. So at the end, percentages will be equal across all generators. There is the generator set metering, generator set protection, and the capacity to load consumption are also part of the genset controller. And then that talks to the engine control module, or the ECM, right? Your car has one of those as well. And that ECM is responsible for the governing, is responsible for the engine protection and the engine metering. So if I were to compare the traditional design or the traditional paralleling to the integrated paralleling. So if you remember the slide that I showed you here 3 or 4 slides ago, we showed a section for every genset controller, a master level controller, and we showed all the different components that are needed to parallel generators. With integrated control, there is no the paralleling is not, even though we call this a paralleling gear, there is no paralleling controls in here. And with no paralleling in the gear, the paralleling is done on the generator set or in the genset controller, right? What we call it is consistent design. It does not change from the code is the same. What we change is the settings depending on the application needs. And instead of running hundreds of wires between the controllers, we only have a handful of controls that are the same that we run from generator to generator and from generator to the paralleling breaker. And obviously this would be easier to learn and operate, and it can be used on both low voltage and medium voltage. A lot of times I get asked, well, what about medium voltage? It's the same. The control is the same. Doesn't care if this is a 4160, 23,000 volts, or 480, right, or 600. Okay, so with paralleling control, the way it works, just going to give you a little bit more information on it. So on this system in here, I have a generator that's right now up and running. The circuit breaker is open, and let's say the bus is already energized and it's at 480. So here's my generator set controller, the one that I just showed you right here. And as you can see, it's my attempt to show you that the two waveforms are not synchronized. So you can see that this is a little bit out of sync, the line side and the load side. And before we close, the circuit breaker is open. We need to match phase, voltage, and frequency. And that happened really fast. So we changed the set point. So the controller is watching both of them and going, okay, now I'm just going to tell the engine, to speed up a little bit to match phase and frequency. And then I'm going to increase or decrease the voltage set point for the alternator, and in doing so, we'll adjust the output voltage. And once the sync conditions are met, we'll send in a signal to the circuit breaker. And by the way, we need to hear that, we need to see that breaker close within 5 cycles. Otherwise, we will lose that synchronization. We won't be able to close, and we won't be able to bring the two together. So we want to close within 5 cycles. And this is very typical of all paralleling breakers, regardless of the manufacturer, right? Whether it's ABB, Schneider Electric, or other manufacturers. And so right now, the blue sign just shows that the two sources are in sync, and the one that's keep waving is how it was before synchronization. If this was a black start or a de-energized bus, okay, so the green that are open, the gensets are not running, we send the generator sets a start signal, they all start. So they all come online and they start, and now they go into this first start arbitration. And the first start arbitration, okay, dictating, okay, which one of those, since there's no master level controller to orchestrate the system, the generators, they do this arbitration, and then one of them wins this arbitration, and that one that wins the arbitration closes its circuit breaker to the bus. The others are always monitoring this load side, and then they can close immediately after, all simultaneously after the first one closes. And then we go from, now their own magnetic fields are coupled, now we go into load share, where the load share is constantly adjusting the voltage and the frequency to match as the load varies. You might say how long this takes, because it took me about a minute or two to describe it. I've seen a lot of applications where we were able to parallel over 37 megawatts in less than 13 seconds for them to come from the time you hit start till the time you have 37 megawatts is about 13, 14 second max. Okay, so now we learn about the energized bus, de-energized bus. So with the integrated autonomous paralleling control, all the paralleling functions that I described are repeated on each and every generator. We need this point of common connection, and we run a few wires from one generator to another. And we describe this now when I talked about distributed logic architecture. So distributed logic architecture is that the brains are repeated on every single generator. That means if one of the generators fails, that circuit breaker opens, it takes itself out of the equation, and the remaining generators continue like nothing happened. You might say, well, no, I don't think so. What if I have my load, I have more load than the gensets can handle? Yeah, that's true. This is why you probably want to have an M+1 system, but let's say that you don't. Then you have to resort into load shedding and shed the non-essential loads. But that's besides the point that I'm trying to make in here, and that is you will not notice a difference. The gensets will not care that they lost one. They won't just freak out and go, oh, I lost one, all the synchronization is going to go out of whack. No, that does not happen. And by doing so, we eliminate single point of failure. So if I have 7 gensets and I lose 1 or 2 or 3, the remaining just continue operation without a problem. So to help you with that, I wanted to provide a specification language, but that would take, it's like I said, and you probably know this because you're designing a lot of these systems. It's a 37 pages long or so, the specs, right? And maybe it's sometime this year we'll probably dedicate a whole session on specs for paralleling controls and paralleling switchgear. But some of the things that you want to have in there is that you want to have, paralleling control panel for each generator set. You want the control logic to be distributed, and then each generator set is capable of starting and paralleling on the bus independently. We don't want a master controller to do so, because if that one fails, that entire fleet of gensets will fail, will not start and will not parallel. They need to be independent and autonomous. That's one of the things that we want to have in the specification. We want to make sure that failure of a system master control. So you might still have, like I said, I showed you a picture in the beginning of this presentation of a supervisory control, right? But we want to make sure that there's a time and place for having a system level controller. And we want to make sure that if that system level controller fails, we don't want the generator set controllers to fail as well. We still want to be able for the gensets to come online parallel and provide loads to our power to our loads if we need to. We want to also have to include a synchronizer, and obviously it's an electronic synchronizer. The same thing with the with the engine control module. It's all electronics, right? We want to have also sync check functions. This goes without saying. Obviously, it's a power. We're closing the two sources, so we need to have a synchronizer and a sync check, and that can all be part of the same one controller. And when it comes to load sharing, because that question comes up, do I want Droop or do I want isochronous? Again, you probably want to resort to isochronous. So isochronous for both kW for the real power and isochronous for the VARs for the reactive power. And we don't want an independent module to do so. We want that to be part of the genset controller as well. And also we need to have some kind of a level of protection as well. I've listed in one of the slides, I've listed the elements and I've listed the ANSI designation and those are the most common elements that you want to have on a genset when you're paralleling generators together. Those are the most common elements or points that you want to have for protection. So again, reverse power, reverse VARs, overcurrent, short circuit protection, obviously, and then under voltage and a few others that I didn't list in here just for space, and we don't have the time to discuss them all. Again, there's a lot of things that we need to include in the specs, so this are just the things that caught my attention from the specs that I'm evaluating right now for a few projects across the country. And that's what I have for paralleling paralleling generators. So to summarize it again, what is needed to parallel generators? To parallel generators, obviously we need 2 or more gensets. We need a point of common connection. That's it. This is the point where the gensets, where the power cables are connected to it. And that could be a collector bus, or it could be a distribution board, and it's either a switchgear 1558 or a switchboard at UL891. We need electrically operated circuit breakers, 1 per generator, and we need to be able to open and close. We need to get this breaker position, so that A contact. The breaker, there will be a breaker charging motor. This is a lot of the manufacturers of switchgear and switchboard. Obviously, they'll include that in their circuit breakers. You need to have a power supply to operate the coils, some kind of a power. Typically, that's CPTs or station batteries. We need to have some bus sensing depending on the voltage, right? If it's a medium voltage, we need to step that down. Obviously, we can't bring 4160 or 13.8 to our genset controls, right? Those operate on lower voltage. And then we need the paralleling functions that I described, the synchronizing, the load sharing, the arbitration, the protection. And what we can do is that we can have all of those integrated on one microprocessor board that's just the size of your iPad, like a 12-inch iPad or so, and that can be integrated on the generator sets. And I hope I was able to convey the message to you of the advantage of paralleling gensets using the integrated control. And now I have one slide about utility paralleling, right? Obviously, when you want to parallel with utility, things get more dicey and more complicated. The first thing you want to do is check with the utility. I can't tell you the rules and regulations for every utility. Everyone is different. You may want to have this discussion at least 6 months in advance. Utilities are not thrilled about you doing close transition. Usually, they even charge an arm and a leg to push you away from doing paralleling. Close transition with the utility, especially extended paralleling. But if you have an extended paralleling application or a close transition with the utility, typically there's hard close transition, which is less than 100 millisecond. There is a soft close, which is just long enough, more than 100 millisecond, but really there's no time. It could be a half a second, could be a little bit more, could be a little bit less, but just long enough to take the loads from one source into another. And then there's extended, where you can be connected for days with the utility, obviously for demand response and financial incentives, right? When it comes to paralleling with the utility, the same thing. Those genset controls, all we're doing is we're controlling the fuel and the excitation. And all we need is just one synchronizer that tells the set points for those generator sets to match the utility. We cannot control the utility. The utility is considered an infinite source. Even if we connect hundreds of generators, right, the utility will be much bigger. Well, I guess it varies from depending on the utility, but typically they're considered an infinite source. In terms of protection, I can't tell you what you need. This has to go, it varies by utility, but there will always be some independent protective relay on that utility main breaker. Have to. A lot of times they might ask for reverse power protection or things like that. The utility does not care about if you cause any damage inside of this application. That's not their problem. That's your problem. They care more about your backfeeding, for example, their side, hurting somebody or causing damage to a transformer that's up here. Okay, and for example, even with the genset controllers that we see in here, the integrated ones, they also are capable with one additional synchronizer on all of just one synchronizer is capable to synchronize numerous generators with the utility. We'll set, again, the set point for the voltage and frequency, and then do the synchronization. I have 3 more slides, and then we'll turn it back to questions. The next 2 slides is just, when you're designing a system, I just want you to use this as a checkpoint for you. I know you have, when you're specifying a paralleling gear, whether it's a 1558 or 891, use this as a checkpoint to make sure that these points are not missed. For example, whether it's CSA, UL, 891, 1558, the bus rating, the insulation, conduit entry, whether the doors are rear or front, hinged, are there door handles, enclosure type, if you need arc flash protection, what is the control voltage? Is it 24, 48, 125 DC, 120 AC? Are we using CPTs? So we have to think about those. Accessories, are there any accessories? And then the number of feeder breakers that we're controlling, is it end transfer switches? And if they're control only or status and control, if there is a remote HMIs in the system, remote enunciators, and what is the connection to a SCADA or BMS system? So use this, print this out, just use it as a checkpoint and say, did I cover all those points when you're specifying a switch gear or a switchboard? And just use it as a reference. Like I promised, there's one case study. This is I was fortunate enough to go visit that site. This is the new Mosaic Stadium in Regina, Saskatchewan in Canada. It's a stadium that can house 33,000 people. It is a 600 volts. They split this into 2 sections, as you can see from the stadium here. So they have 10 generators that can feed power half the stadium, and the other 10 gensets for each side. So every 5 will parallel together. They just wanted to parallel the generators, and they wanted to have capacity to load consumption optimization. So the solution here's to use. For every side of the building we will have 5 generators, 500 kilowatt each, and to use the integrated control, the one that I just described, the paralleling control. They're containerized, so they're mounted outdoors with the NEMA 3 enclosures. And then the controls are the ones that are by the way, the paralleling circuit breaker was an onboard, so it was a skid-mounted paralleling breaker. And then the control on the that control that I described is the one that was responsible for controlling the circuit breaker. And then it was pre-wired from the factory to do the sensing on the line side and the load side. And then there was only a few cables that we needed to run for load share and first hour arbitration from generator to generator, and obviously the power cables that will go from the enclosures that you see in here into that point of common connection. And this takes me to my last slide course summary. I hope you enjoyed this course, which is specifying generator set paralleling controls. In summary, I just want to say that when you're writing specs, write specifications based on functions and performance, specify integrated paralleling and protection control, specify paralleling control architecture redundancy, capacity to load consumption optimization if you want to reduce wear and tear and fuel consumption. And at the end, I just added this recently, is request a paralleling demonstration of course, with COVID and all that, things are a little bit hectic right now, but then request a paralleling operation to see from the factory to see how paralleling is accomplished and do a site visit if possible. And with that, I want to thank you and turn it back to Gary.
Thanks so much, Hassan. That was all fantastic information. And now comes the fun part where you get to answer some questions from the audience. If you do have questions for the presenter, please type those into the Ask a Question box on your screen. We'll get to as many as time allows. We probably won't get to too many today. We've got about 10 minutes, but questions that we don't get to will be posted online at www.cscmag.com. That's www.cscmag.com. And remember, to download a certificate of completion or a copy of the presentation, just use the Event Resources tab on the left side of your screen. All right, Hassan, you ready to go?
Yes. Let's do it.
All right. Let's start with, what are the cost differences between onboard paralleling and PLC-based systems?
That's a great question. Thank you for sending that. Thank you for sending that question. Usually don't talk about cost during these technical seminars or technical events. I would, ballpark number, I would say in the round of $100,000. The difference between using a PLC-based versus this onboard paralleling. And this is just the cost of the equipment and the wiring and whatnot. There are other things also in there. You will reduce real estate. If you want to do the traditional paralleling, you need one section dedicated for every genset control, and then which that is eliminated with the integrated paralleling. And then there is a need for a master level control. And then the other thing is that you might be caught in the middle of a lot of finger pointing between, okay, whose problem it is to handle is the problem in the genset control, or is it in that synchronizer that's in the switchgear, or is it somewhere else?
Makes sense. How about, can you perform manual paralleling with the integrated paralleling?
Okay, so actually that's a good question, and I believe that question comes up a lot, and it's the impression that if I have this integrated paralleling, I cannot do manual paralleling. Yes, you can do manual paralleling, and you will be able to. It's not in the sense manual. It is auto manual. It's manually initiated. However, the synchronization is done automatically. I can assure you, even if you specify the traditional paralleling, you're still not going to be able to do the manual paralleling that you're thinking of, because you're still relying on the ECM, which is an electronic controller that is on the engine and still a voltage regulator. So by doing so, by using this traditional paralleling, and we think that we actually are able to do this manual paralleling because we think it might be safer. I've looked at a lot of projects. I've looked at a lot of the wirings that's been done. It gives us a false sense of reliability, or a false sense of that I'm getting manual paralleling, because at the end of the day, you're actually still sending signals to those controllers that are on the engine and the generator. I was able to answer. Yeah.
Sure. Yeah, that's great. Thank you. So what happens if a genset controller fails when a parallel system is running?
Yeah, so that was okay. One of the slides I mentioned that, and it's a very good question, and we should repeat it here again. Is that, again, if I have a fleet of generators, right, and this is what I described as a distributed logic architecture, so the paralleling functions are repeated on each and every generator. If one of the gensets, genset number 2, for example, just fails for whatever reason, that controller opens that circuit breaker and takes itself completely out of that equation, and the remaining gensets will continue the operation seamlessly. So we will not see, we won't see the entire fleet of gensets failing. We will not see things going out of whack because we have one genset controller that failed for whatever reason. Or maybe, it's not just genset controller. You might have a fuel bubble, a bubble in the fuel, where it causes one, or in not clean fuel that's going into the genset just causes it to fluctuate back and forth. And so in that case, we might have a problem. That genset takes itself out and the system continues running.
Got it. Can you apply the integrated paralleling to medium voltage systems?
Yes, it can. So it's not just for 480 or 600 volts. We don't care if it's a 4160, 13.8 or higher. That's the power aspect, right? The controllers are independent. They're just doing the synchronization using the zeros and ones, and using a lower voltage to do that. And that the power sections are independent of the paralleling.
Got it. Is it possible to parallel generators from different manufacturers?
It is possible. I would say if you have a project that you're working on with gensets from different manufacturers, please reach out to your support personnel from that manufacturer, whoever you're working with, to discuss. I'm guessing this question also meant that I'm guessing that it didn't mean I want to buy one genset today from this manufacturer, and at the same day I want to buy it from a different manufacturer. I want the two to parallel. I'm guessing the person who asked this question is I have an existing gensets. I want to buy 2 more, or I want to add some more to my gensets. You can. We have to worry about, if you remember, let's not forget this. This is very essential. The alternator, whether it's a 2/3 or a 5/6 pitch, so it's the pitch of the alternator, please check on that first. If it doesn't match, there are ways around it. And then we have to think about the controls, load sharing, and then if we're taking load on and off, load rejection, how the ECM handles the fueling to the engine. So it can be done, not a problem, but let's have a discussion ahead of time.
Sounds good. Just a few minutes left here. Let's go with, how do you ground paralleled systems?
Okay, so that could take us an entire day.
Maybe a bigger question than we have time for.
Yeah, well, maybe quickly, I'll just say for low voltage, I'll make it simple for parallel system. For low voltage, you have to bring in the neutral from the generators into the distribution board, and there you'll connect, hopefully, the neutral to ground bond in there for low voltage. For medium voltage, what we typically see is the neutral grounding resistors are used, and then you typically have 1 per generator. That's how it's typically done with parallel system.
Got it. And let's just do one more question here. I think that's about all we have time for. Do we have to provide sync equipment with 2 generators in parallel, both starting at the same time?
Not if you specify the integrated ones. You don't have to have sync equipments. That genset controller will have all the synchronization, that little board that I just showed you a picture of. Like I said, this is the size of your iPad. It has everything in it to do the synchronization and sync checks and the protection and the load sharing between the generators. So you would not need to specify any additional sync equipment. And hopefully that will help you. So if we can take that off your mind, then you can focus on other things when you're designing the system.
Got it. Thank you, Hassan. Thanks for all the great questions to everybody in attendance here. And of course, thanks again to our speaker, Hassan Obaid, for sharing his time and expertise. Thanks, Hassan.
Thank you, Gary. Thank you very much.
I'd also like to extend a special thanks to the sponsor, Cummins, for sponsoring today's event. And now that we're just about done, we're not quite done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete that because we use that information to help improve future webcasts. Finally, on behalf of Consulting Specifying Engineer and CFB Media and Technology, I'd like to thank you for attending. This is the end of the webcast. Thanks, everyone. Goodbye.